Thank you. And thank you very much for the invitation. My name is Paweł Mazurek. I'm going to present you results of a joint work which was done with Mate Farkas, Andrzej Grudka, Michał Chrodecki and Michał Studziński. It's going to be mostly about absolutely maximally entangled states and properties of codes that one can derive from them. But the reason I'm here and I'm talking about this here is that networks generated by absolutely maximally entangled states were proposed as a toy model for ADS-CFT correspondence, as they quite naturally mimic many properties that are desired in this correspondence. So first, what do I mean when I say absolutely maximally entangled state? We are going to have n-particle system with local dimension d, and then if we have this property that no matter what part, no matter how I divide my system into two parts, if I trace out the larger part, then the smaller part will be in a maximally mixed state. So this statement is equivalent to the statement that the entropy on the smaller part of the system is maximal, and it can be shown that this enforces the form of the state to be the following. We have on the smaller part of the system, B side, we just have a sequence of all possible vectors of length m and taken from the alphabet of size d, and here there are states that are orthogonal to each other on the larger part of the system. And of course, if you have such a statement, then if you show that a state satisfies this property for some m, then it naturally satisfies it for all m's smaller than this m, because you just trace out identity and you obtain identity. And this notion is a generalization of K uniformity, in which you just demand that this property is satisfied on the smaller number of on the smaller subsystems. And now, why this is the figure showing ADS-CFT isomorphism correspondence that I don't know much about, but I somehow know about properties that it satisfies. So the goal is to connect operators that act in the bulk with the operators that act on the boundary here in the lower dimensional space. And one of the properties desired is that the mapping between the operators in the bulk, that's local operators, mapping to the boundary, it's not unique. Also, there are different properties. We desire that the entropy of the state on the boundary, on a selected subregion on the boundary, it should be proportional to the length of the geodesic, so the shortest path in the bulk. And it's especially this first property, it resembles error correction code setup, in which you just encode some of your information into the subspace of the system on the boundary, and then this encoding is not unique. So you can encode it into like this part, or some subsets of the green region, but it's not determined where you do so. And by satisfying this property, you also allow for this encoded version to commute with all local operators on the boundary, which is this error correction thing that you have local errors, and then they should not influence your logical information encoded in the boundary. And seeing this, first Daniel Harlow and his collaborators proposed that it should be connected with quantum error correction schemes, And then this idea was developed in this paper by generating these error correction schemes from networks of absolutely maximally entangled states. And why absolutely maximally entangled states? Because they have this property that if you in fact construct, we discretize the space here, and we imagine that such a pentagon, this is an absolutely maximally entangled state, and all legs that are free, that are on the boundary, they are qubits. They form our system on the boundary. And all absolutely maximally entangled state, they define a map between all legs, all input legs to all output legs, and it does not matter which is the direction of this mapping. So as long as we encode information from the interior of this lattice to the exterior, the number of legs is increasing, then this mapping will be preserving a scalar product between encoded information. And this property that it doesn't matter to such extent how I define this direction of encoding, unless it's to the exterior, it reflects the fact that the information from this point, from this red point, it can be encoded like here, or it can be encoded here. You can to some extent you can choose where it goes. Yes?
These are qubits, and on your previous slide you had e-bits.
Yes. You can imagine just that that there are qubits as well. Yeah.
No, it has to be qubits because there are no absolutely maximally entangled states for certain numbers of qubits.
Yes, but for qubits you have for 2, 3, 5, and 6, and this is exactly this case where you have 6 legs, counting this red one. Mm-hmm.
Red ones are red.
So the red one, I treat the red point as this input leg as well. That is just hanging there, ready to accept my information that I want to encode in the boundary. Mm-hmm.
So can you explain this tiling here a little bit further, please? Where does that come from? Why is this tiling exactly the way it is?
So the tiling was chosen to be so because we know that absolutely maximally entangled state for 6 qubits exist. So I need every structure to have 6 legs. Sorry, here we have 5 legs coming from the sides, and 6 is upside. So it's a tiling of the pentagons, and I just know that such a tiling exists. In fact, it's quite arbitrarily suited for the AME state that I want to use.
Is it critical that they're between neighboring tiles?
Uh-huh.
Is it critical that the edges are between neighboring tiles?
You mean this point?
No, I mean, this is a planar graph.
Yes.
Is that a particular property that you use?
No, I don't think so. No.
Okay, thank you.
So first I will describe properties and ways how to generate absolutely maximally entangled states, and then at the end I will come back and show that these properties influence properties of the ADS-CFT correspondence that we want to have. So for 2 qubits, the case is simple. This is when you trace out one of the bits, then the remaining part is maximally mixed, and the same for 3 qubits. But already for 4 qubits, the case is complicated, and in fact it can be shown that maximally entangled state does not exist in this case. It was shown in the way that one was trying to, in fact these authors, they shown that it's not possible to obtain maximally mixed state on every bipartition of the system. Then yeah, this is just example that you try to generalize this to 4 qubits, and it does not work because this is not identity operator. Now for 5 and 6 qubits, the states exist, and they were originally obtained in the same manner, like numerical searching. Also for it's known already for some time that for n larger than 8 they do not exist, and there was a quite recent result that for 7 qubits absolutely maximally entangled states do not exist as well. But there is a hope because of the connection between absolutely maximally entangled states and quantum secret sharing schemes. We know that if you increase local dimension enough, then for any number of qubits there will be absolutely maximally entangled state. And this connection, somehow intuition behind this connection is depicted here. So in quantum secret sharing scheme, the goal is to, when you have a collection of 2M systems, to encode information from one system to the rest, to this 2M-1 subsystem, and then you need them to be able to decode this information only if at least half of them cooperate. If just one of the parties or less than half of the parties decide to cooperate and recover the information, then they should get no information at all. So this is somehow a reflection that the reduced state is maximally mixed. So let's say that we want to encode a secret state from 1 qubit to the rest of the qubits, and this is just one code word of this code. And then using the form of the absolutely maximally entangled state, which is like this, I just showed here the system B1, which is the encoding part. Because of the fact that these vectors they are all orthogonal, if these parties gather and they are able to perform some joint unitary, then they can retrieve this information on a selected bit. So this is the state. This is the code word before the unitary, and sorry, U is missing here. And this is the result of the some unitary applied to this state, and you retrieve a state I at some selected qubit, and at the end you have your message on the party.
Who are the people who are cooperating here?
The cooperating part is A system. So this is shown in the case that the these numbers are equal, but in general it works as well that you just assume A is bigger than B. So sufficiently number of collaborators are following the procedure. And finally, the property that will be the most important for us here is that the relation between absolutely maximally entangled states and isometries. So when a state is absolutely maximally entangled, then in some basis, in some division to subsystems NAB, it can be written in such a basis. But then, if you rewrite this tensor as a transformation matrix, just from states B to A, and here you use the same coefficients as in this decomposition, then you can show that as long as this state is an absolutely maximally entangled state, this transformation will be isometry, so all inner products will be preserved, and vice versa. For isometry, you just demand this property, and for state reduction of this general form, you have this relation. And here, because the state is maximally entangled on every cut, every division, it does not matter which subsystems you treat as the outputs to the map and which subsystems you treat as outputs of the map. So it's quite general here.
Is it obvious for me? Sorry.
Mhm.
Is it obvious for me that I should see that this is maximally entangled?
So sorry, can you repeat? So this maximally entangled part, it comes from the fact that this property has to be satisfied for every division of the system into A and B. This is this. Mm-hmm. And the thing that we want to mimic in this toy model is when we would select some part of the edge and some subsystem on this part of the edge, then we would like to easily recover the property that the entropy of this subsystem is just proportional to the length of geodesic connecting to ends of the subsystem, and the measure of this length is would be just number of this contracted